Hello. Last time we'd seen this video in order to understand higher order integrals. Today I want to show the usage of a tool called Geozebra, and we will be solving a practical question pertaining to the PhD course. So we'll first head on to the question where we are given this uniform joint PDF in 2 dimensions where this function is z is equal to this function of x comma y, which is 1/4, and the x range is between 0 to 2 and the y range is between 0 to 2, and otherwise everywhere else this function is a 0. And then we are given this question that if we given this region A where x and y is less than or equal to 2, we want to find out the probability of A. To understand this, we head on to this tool called Geozebra where I have put in some functions. So the first function which I've defined, which is the PDF of the uniform distribution in 2D, is this function of x and y, where the support has been defined between 0 and 2 and 0 and 2 for x and y, and the z value is 0.25 within this region and 0 everywhere else. This is some specific syntax which Geozebra requires. So I put this: if these conditions are met, then the z value, which is the functional evaluation of x comma y, is 0.25, otherwise it's 0. So if I enable this particular function, you can see that this is nicely plotted, this specific shape where the x-axis is going from 0 to 2 for this shape, the y is also going from 0 to 2, and the z value is a constant 0.25. Everywhere else we have a 0. Now if you try to reproduce this experiment, this particular code, you might not see visuals like this. You might see something similar because I have not tweaked some settings. So if I had to show you some of the settings, I have kept some the min max of the different values of the different axes to be something more sane so that the visuals are better. Now if you note that the min value of x for this particular uniform distribution is 0 and the max is 2. So I've gone slightly to the left of 0 and slightly to the right of 2 for the x-axis. Similarly for the y-axis, and for z-axis I've gone from 0 to something close to 0.55. Now the next part of the question, which is we have to plot this region where x plus y is less than or equal to 2. Now importantly, again, we have to ensure that 0, so x lies between 0 and 2 and y lies between 0 and 2. Now if you have to visualize this region, I have defined another function which has this additional constraint. So 0, x is less than 0 to 2 and y is between 0 to 2, and x plus y is less than or equal to 2, and if all of these conditions are met, then the z value or the functional evaluation of g for that x and y is 0.25, otherwise it's a 0. Now if I enable this, you can see that this is like this triangle in this 3D space. We can also view this from different angles. So if we look at this in an xy plane, you can see that this is a triangle. We can also view this in a, let's say, a yz plane or a xz plane. So we can view this in the different planes. Now we want to basically find the area of this 3D triangle. Now without solving, we could very easily see that if we first see the area of this structure, this uniform distribution, we know that the area under the curve has to be equal to 1, and we can also very easily verify that. So the height of this surface is 0.25, the length is 2, and the width is also 2. So we can see that 2 times 2 times 1/4 gives us a 1. And now if we enable this function g of x comma y, we can see that it's symmetrically dividing this cuboid like structure into 2 parts. So the area under this curve has to be 2. So we'll keep that as a sanity check, and we can very easily intuitively understand this. Now the question, if we had to, this is a trivial example, if we had to solve more complicated examples, we can still use the principles from this discussion, which is we want to be now solving this higher order integral. Now before going into the maths, let me first show you a visualization by enabling a few things which I have created. Okay, so first we'll see that if we fix our view to this YZ plane, we can see that we have drawn this rectangle. In this case, it's not appearing like a rectangle. So if we actually go to the XZ plane, I think that would be better. So we go to this XZ plane, we can see that we have this rectangle. So in this XZ plane, if we fix the value of Y, we can see that we have this function of only x because y is fixed for now, and this function of z is 1/4. Now we can very easily compute the area under this curve, where this curve is 1/4 constant and x is varying from 0 to some number here. Now that number is given by the fact that we know that x plus y is less than equal to 2. So if we fix the value of y to, let's say, 0.6, so we can see that the value of x is 0.6. So then the max value of x we can get as per this constraint x plus y less than equal to 2 is 1.4, which we can also clearly see here. So when y is 0.6, then we get this rectangle whose width is 1.4, and we know that the height is 1/4, which is the constant. So now we can very easily compute the area of this rectangle, which is 1/4 times this 1.4, which is the width. Now we can also see that this is for a specific y equal to 0.6. If we just use a general y, then this would have been the area under this curve would be 1/4, which is the height, and then 2 minus y, which is the width. And essentially now, in order to calculate the area of this 3D triangle, what we will do is for a fixed value of y, we'll find out this area of a rectangle in this XZ plane, and then we will vary the y going from the minimum y0 to the maximum y2. So let's just view this animation and we'll be able to appreciate the 2D integration in this case. So we can now see that now the y value has changed, the corresponding rectangle has changed. So currently we have y equal to 1.35. So therefore the x max would be 2 minus 1.35, and we can verify that. Correspondingly, this area is smaller, and this is what this particular video had also shown. So in the first case, we solved this 1D integral in this XZ plane, where the height with the function is a constant 0.25. And in this simple case, we have x varying from 0 to 2 minus y. So we can first view that as the inner integral. We have this function of xy, which is a constant 1/4, and we have this first integration over the x-axis, which is this integration of limits from 0 to 2 minus y of a constant function. So therefore, we just directly get the value of 2 minus y when we put those limits. Again, we could have not used calculus, and we could have directly seen that this is a rectangle. We know that this is a specific shape is a rectangle whose height is 1/4 and the width is 2 minus y. So 0, and here we have the other limit is 2 minus y. So we could have directly written that the area shown in this dark region is 2 minus y. And then that's the inner integral, that's this inner rectangle area that you found out for a specific value of y. And then the next thing you want to do is to vary the y. So the next thing you'll want to do in this integration is, once you've found out the area of that particular slice of the rectangle for a fixed value of y, now you want to integrate that over y, which is something similar to if you just run this animation and then you look at the different slices produced, and then you are computing the integration over the y variable, which would then be the integration of this over y from y going from 0 to 2 of this function of y, which is 2 minus y. And then if you do simple calculus, you'd be able to see that this p of a is a half. So this was to show you this very intuitive tool where I have defined these two 3D functions. The first function was the uniform PDF in 2 dimensions. The second function, the first function is this uniform PDF in 2 dimensions. We can nicely rotate and see the different views. The second function was the specific constraints over which we want to find out the probability. And we can see that this is this 3D triangle. We know that the area under this curve has to be, sorry, the volume under this curve has to be half. And next we created this slider, and then I created various attributes, various properties to help you nicely visualize this. So I'm mainly creating this polygon around this slider as an input, and we can see the different endpoints of this polygon. We can see that the z is going from 0 through 0.25, and then we can see the x limits going from 0b to 2 minus b, and we can then nicely visualize this. Now, as an exercise, you could, instead of first fixing the y value and then finding out that area of the slice under the xz plane, you could do the reverse. You could fix a x value, and then you will have the integration, the order of the integration changed, but the answer should still be the same. So hope this gives you a nice glimpse of how we can understand higher order integrals using the simple principles of first finding out the area or the volume of, so in this case, the area of a slice in this specific 1D case, and then you move that slice over the other dimension to find out the volume.